Assalamu alaikum. So in this video we'll continue with the implementation of rotor flux oriented vector control. Now if we need to implement the vector control, we need a method to calculate the reference current in the QD axis, because if we recall, in flux oriented control we found that omega slip is equal to 1 over tau r IQ SE over ID SE, and we found that the torque TE is equal to 3 over 2 P over 2 Lm square over LR IQ SE ID SE. So we need to find the reference current for the torque component of the stator current, and also we need to determine the reference current for the flux component of the stator current, and so we can calculate omega slip, and from the knowledge of the speed of the motor we can calculate omega synchronous, where omega E will equal to omega R plus omega slip. So theta E is equal to the integration of omega E d tau, which will equal omega R plus omega slip d tau. So we need this angle in order to do the transformation either from ABC to DQ or from DQ to the ABC. So for example, if we can calculate the reference current IQ SE reference, ID SE reference, we can use the transformation matrix from QD0 to the ABC in order to calculate the reference current in the ABC reference frame, or in the machine variable, let's say. IA star, IB star, IC star. And after that we can use current control in order to regulate the current inside the motor. So here we can plot the indirect vector control block diagram, and we start here with omega R reference, which will compare it with omega R, and after that we need speed control, which is PI, and this one is speed controller. After that we can use saturation, and the output of the speed control is torque. Actually it's proportional with the torque, so this TE reference. So if we have ID SE reference, which we can calculate from the rating condition of the machine, we can multiply it by the constant, which is 3 over 2 P over 2 lm square over lr. Then here we can divide the torque over the constant, multiply by IDS, and now we can generate the reference current, which is the IQS reference. So now we have the IQS and we have the IDS. We can do the transformation from QD to the ABC. Of course, we need the knowledge of theta E. Now, in order to calculate theta E, we need the IDS and we need the IQS. And here we can calculate omega slip, which will equal 1 over tau r IQS star over IDS star. And this will give us omega slip, which will be added to omega r. Now, if we integrate it here, we're getting theta E. Now, after that, we can have the IA reference, IB reference, and IC reference, and those can go to hysteresis current control. Current controller, which is actually a nonlinear control, and this will give the gate pulse for the inverter N6. Now the gate pulse will go through the gate driver, and it will synchronize the switches in the inverter, where here the machine is connected. This is the induction machine. Now we can measure the speed using tacho generator, and this will give omega r mechanical, so we can multiply it by P over 2 in order to get omega r electrical. And here we need a current source inverter, this one. So this is the overall block diagram for what we call it indirect vector control. Now, what we need to discuss the hysteresis current control. And control. Now this is current control. Simply here we can compare I star of I. If we compare it with I of I, the actual current, where the actual current we need to measure it and feed it back here, by the way. So simply here we can measure the current. Uh, by the way, we can use two phases, and we know that IA plus IB plus IC equal to 0. So simply if we measure only two phases, the third phase IC, for example, can be equal to minus IA plus IB, and this will reduce the cost. Now here we will generate the error signal. This error signal will go to hysteresis band. And after that, we are generating gate pulse for the switch S, let's say, high of phase I. And the complement of that will be the gate pulse for switch, the lower switch of phase I. And I is element of A, B, and C. Now the gate pulse here, so S IH, for example, will equal to 1 if I less than or equal I star minus delta I, and 0 if I is greater or equal I star plus delta I, where delta I specify the hysteresis band. So here we can give an example. Let's assume that we're having the following reference we need to track. Now the idea in the hysteresis current control is to draw two boundary, let's say, above and under the reference or envelope, in order to encapsulate the reference. So simply for us, this one is II reference. Now the idea in the hysteresis control is to force the current to enter inside the envelope and stay there forever. So if this is the actual current, the hysteresis current control force it to enter inside the envelope and to stay there forever. Now, how to generate the gate pulse, or how the gate pulses are generated here. Simply, let's assume here, and let's discuss it here, and here, and so on. Let's discuss it also. Let's start from here. And I think this is enough to highlight the idea. Now, if in this point the current is less than or equal the reference current minus delta I. So delta I is the boundary. So in this case, the logic will be 1, and this will continue until we are hitting the second boundary, where the second condition is satisfied. Here the current is greater, actually here is equal to I star plus delta I, so delta I is the window. So simply here we have this from here to here is delta I. The same thing here, from here to here is delta I, and this is the side, the current rebel. So at this point, the second condition is fulfilled, so the gate pulse will be 0, and it will continue until this point. At this point, the current is touching the lower boundary, so the gate pulse will equal to 1, and after that it will hold until touching the opposite boundary, then it will be 0, then it will be 1, then it will be 0, and so on. This is how to generate, or this is how the gate pulses are generated in the hysteresis current control. Now, you should understand that the hysteresis current control is nonlinear current control actually. But the hysteresis current control is very fast, but suffer from a variable switching frequency. So simply in the hysteresis current control, the switching frequency is variable. So here it suffers from variable switching frequency. Now, the ripple current is decided by the window. If the window is very, very small, then the ripple current is reduced, but the switching frequency will be very high. Now, sometimes we can use a PI current control with pulse width modulation, which is a linear controller, instead of the hysteresis current control, which is the nonlinear control. So now, if we use PI current control plus pulse width modulation, and this actually will be a linear control. While the hysteresis current control is nonlinear control, bang bang control. So simply, what's that? Here we can say the I star, we compare it with the actual I, then we are passing the error through a PI current control, and you know that the PI current control is the most famous actually linear control used in the industry because of the integral action. If you can design the current control such that the system is stable, you can guarantee that the steady state error due to unit step input is equal to 0, which means that the actual current in the machine equal the reference. And now this will be the V star that we can compare with a carrier, and this will generate the gate pulse for the upper switch, and the complement for that will be the switch for the the lower switch. This is in general the idea behind the PI current control. But however, in the vector control we cannot use the IA, the IA, the IB, the IC, the reference currents in the machine variable, because they are alternating, and simply the PI control will suffer from the tracking accuracy. So the best is to use the PI control in the QD reference frame. Why? Because in the synchronous rotating reference frame, all the sinusoidal signal that are rotating in synchronous speed is seen as constant. So simply, this means that here we'll use the Q and the D component of the current and regulate it. And how we can do that, let's highlight it here. So let's start from the speed control. This is omega star, that if we compare it with the actual omega, then this will be a PI speed control. This will be the torque TE star. If we divide it over the constant, which was 3 over 2 P over 2 Lm square over Lr, and here we have the IDSE star. Now we are getting the reference current in the QD reference frame, which is the IQS star and the IDS star. Now here we will do the current control. So here we'll compare this one with the actual IDS, and here with the actual IQS. Then we will use a PI control here and a PI control here, and this will generate the VQS reference, and this will generate the VDS reference. And you know, the machine can't understand the QD reference frame. The machine only can understand the machine variable, the ABC reference frame. So here we need to do the transformation from the QD to the ABC, and now we can generate VA star, we can generate VB star, and we can generate VC star. Now VA star, VB star, VC star will go through the pulse width modulation in order to generate the get pulse. Now here we need, of course, theta E, which can be calculated from the IDS and IQS, where we can calculate omega slip. Then we will add it to omega R. Then we can integrate it here, and this will be the theta. And you know that omega slip is equal 1 over tau R IQ S star over IDS star. And simply here we can take the IDS star, and from here we can take the IQS star. And omega R actually is from the machine. So now we need to find the IQS IDS. Now if this is the inverter, here we are using a voltage source inverter, and this will be the induction machine, where in the first stage here we can measure the speed, taco generator, and the speed can be connected here and here, after multiplication by p over 2. Okay, or let me reorganize it. It will be more better, but you are getting the idea, I hope so. So let's continue with the current. In order to calculate the current, we need, this is IA, this is IB, this is IC. Here we need a transformation from the A, B, C to the Q, D. And now here what we having? We have I, Q, S, E, and here we are getting what? I, D, S, E. So simply now we have the I, Q, S, E, and we have the I, D, S, E. And for the speed, this will be the tacho generator, and this will be the shaping to convert the mechanical to the electrical. And now we can close the loop here and here. And this is actually also indirect vector control using LPI current control. So this actually, let's write it here. Here, this can be seen as indirect vector control using PI current control. Now this is a linear controller actually in terms of the current control, and this is the nonlinear current control. Now your homework is to simulate the indirect vector control field oriented vector control for the both cases, when using the hysteresis current control and using the PI current control. For for the two current controllers, and this is due to let's say next week. So you have 1 week from today. So stay safe and good luck. Hope to see you next time in the classroom.